We're going to be approaching our introduction to number theory from two different directions. All right. On the one hand, we're going to use it as a vehicle for introducing methods of proving mathematical statements. And on the other hand, we're going to see how it can be applied to practical fields like cryptography and the design of algorithms. So our approach is going to follow the general model that you see in advanced math classes, where you start with a definition, then look at theorems that tell you things about the definitions and how they connect back to earlier ones. Then you prove the theorems, and finally, you look at ways that the theorems, the concepts, the definitions can be applied. So what exactly do we mean by a proof? A proof is a series of valid arguments that leads to a specific conclusion. For example, I have here a valid argument form that we saw earlier in the class called predictively the transitive property or transitivity. Now, to show how this is used, I'm going to apply it to solving this algebraic equation. Right now, I know you're accustomed to doing this kind of thing literally in one line, but I'm going to write out the process in much greater detail than we normally would, just to illustrate what the logical basis of it is, so you can see how it connects back to this transitivity form. Right? I would start this with if x minus 3 equals 6, then x minus 3 plus 3 equals 6 plus 3, because we can add a number to both sides of an equation. That would be my first step, right? My second step, I'm going to continue on from there. If x minus 3 plus 3 equals 6 plus 3, then x equals 9, because 6 plus 3 equals 9, and x minus 3 plus 3 equals x. All right, so what can I conclude from this, right? Well, what is my conclusion? It's going to be, therefore, if x minus 3 equals 6, then x equals 9. Now, like I said, I realize you would never go into this much detail in an algebra class, but if you compare this sequence of statements to the transitive property, you should see how my argument here on the right matches the logical form on the left. X minus 3 equals 6 is the P. This x minus 3 plus 3 equals x plus 3, that's the Q. Then I repeated that Q part down here, and x equals 9 is the R. Right? With those substitutions, you can see how we were able to logically conclude that if x minus 3 equals 6, then x equals 9, or if P, then R. Right, so you can also see the kind of general format that proofs will have here, right, where every logical step is followed by some kind of explanation. Those are the because parts here. All right, so in many ways, proofs are kind of the word problems of higher math, right? And in its own way, each one is unique. So there's no way to give a general formula or procedure that will work in every case. There are, however, a few general guidelines that you should always keep in mind. Right, so with the first one here, when I say a proof should be complete, what I mean is that you should always be explicit about things you're defining and using. For example, if you need to use a variable to represent, say, an even number, then you should explicitly state that. For example, with a statement like, let n be an even integer. Right. Now, the second line here, every step should have an explanation. For example, if you're justifying something with a definition, like the definition of an even number, you could say, by the definition of an even number, or if you're referring to a specific formula or theorem, you could say something like, by, for example, we're actually going to look at this one later in this chapter, by Bezout's identity. And then you state what you're concluding from that, right? So if you're using a previously proven theorem that wasn't special enough to get its own name, then you could just paraphrase the theorem. For example, since we know that all differentiable functions are continuous, we know that, or we can conclude that, right? And you state your conclusion. Right, now, with respect to the general format, you're going to see some things like the two-column proof that you may remember from geometry here in this class, but those are really only used as teaching tools. Right? When you're writing an actual proof, it should be done in the standard sentence paragraph kind of format that you would use for any other kind of writing. So for the sake of clarity, it's a good idea to mark the beginning of a proof with something like proof, and then you start, right, and to end it with some kind of a closing phrase, like which is what we wanted to prove, or say something like QED. Something that makes it clear to the reader that you're finished, right? QED, that stands for the Latin phrase. It's quod erat demonstrandum, which means which was to be shown, right? And it's a common abbreviation used to mark the end of a proof. All right, so not following number 5 here is a mistake I occasionally see algebra students make. When you're writing an equation or series of equations, each one should be on its own line. For example, I would put x minus 3 on its own line, and then on the next line, x equals 9. Sometimes I'll have an algebra student try to write like the 10 steps in a solution to an equation all on one line as if it were a sentence, right? And that's just exceptionally hard to read. And finally, looking at number 6, the language of mathematical proofs it can be almost stylized in its choice of words. Little phrases like let, or by, or since we know, or here by definition, right? And many others are used repeatedly in mathematical proofs. Now, there isn't a comprehensive list of these, but if you just kind of stay aware of this as you read and listen to mathematical proofs, you'll see things like this come up over and over again, and that you should just start using in your proofs as well. Okay, so what's next? Right now that we've got kind of a general idea of what we mean by a proof, and kind of we've seen an example of how the logical forms that we've talked about in the last couple of chapters tie into these proofs. In the next lecture, we're going to look at mathematical definitions, right? Mathematical definitions have a very specific format that we use. So we're going to see that format and what that format implies, right? So you'll get an idea of why it's important.